So yesterday we discussed about the moment of inertia and radius of gyration. Today let's see the next part of the theory and the problems. Okay. So now let's talk about the relation between linear and angular quantities. So what is relation between linear and angular quantities? So let's suppose we have a particle which is performing circular motion. So in some time it moves from this position A to this position B. Okay, so it moves by this much distance over the arc of that circle. Okay. So we define a quantity called angular displacement. So for that we need to know the relation between angle and the length of the arc. So angle is defined by the arc length divided by radius. We know this. Okay. From 11th standard, first chapter, second chapter actually. Okay. The units and measurements. Okay. So angle is S divided by R, where S is the length of arc and R is the radius. Then I'm sorry, the angular displacement theta bar. Okay, so we are defining a quantity called angular displacement theta bar just in the same fashion as that of linear displacement. So angular displacement is given by what? It is the angle covered by this particle when it performs rotational motion or circular motion, and the relation between the linear displacement or the tangential displacement S bar and this theta bar is given by this formula. So S is equal to what? Theta bar cross R. Okay. All right. So it is the vector product of theta and R, not in the other way. Okay. It's not R cross theta. It is theta cross R. So this is the important thing. After that, this is a vector quantity. So it has magnitude as well as direction. Okay. So to find out direction, we make use of the right hand thumb rule. So what is right hand thumb rule? So take your right hand, put that right hand in direction of the first vector. Okay. In direction of uh, your radius vector, and curl your fingers towards the motion of particle, in direction of motion of particle, and stretch your thumb. So your stretched thumb will give you the direction of angular displacement. Okay. So here the particle is moving in anticlockwise sense. So the direction of its angular displacement will be what? The outside the plane of your device. Okay. If you take your right hand, curl the fingers in direction of motion of this particle and stretch your thumb. Okay. Then we find angular velocity. So angular velocity is rate of change of angular displacement with respect to time. Okay. And its average value is given by theta upon t. So if you want instantaneous value, it is derivative of theta with respect to time. If you want average value, it is just theta divided by t. Okay. Yeah. Hi Abhishek. Okay, you are back. Good. All right. So then this is angular velocity. Just like we define linear velocity, which is rate of change of position with respect to time, angular velocity is rate of change of angular velocity, angular displacement with respect to time. Okay. After that, we define angular acceleration. So what will be direction of angular velocity? It is in same direction as that of angular displacement. So take your right hand, curl the fingers in direction of motion of your particle and stretch your thumb. So stretched thumb will give you the direction of angular displacement and also the direction of angular velocity. Okay. Then if you want angular acceleration, so just like linear acceleration is change in velocity with respect to time, angular acceleration is change in angular velocity with respect to time. Okay. So instantaneous value is derivative of angular velocity with respect to time, and average value, if you want, it is final angular velocity minus initial angular velocity divided by final time minus the initial time. Okay. So now there are two kinds of accelerations in circular motion or rotational motion. So first one is centripetal acceleration, which we had discussed when we discussed circular motion and uniform circular motion. And there is another acceleration which is known as tangential acceleration. So tangential acceleration is alpha bar cross r bar. That is angular acceleration, the cross product of angular acceleration and the radius vector. Okay. And in magnitude, tangential acceleration is given by what? It is r into alpha. This is the magnitude because both are perpendicular to each other. Alpha and r are perpendicular to each other. So the magnitude of the resultant is magnitude of one vector into magnitude of second vector multiplied by sine of the angle between two vectors. Okay, and angle between them is 90, so sine 90 is 1, and that's why 80 is equal to what? R into alpha. Okay, now here is an important point, that this tangential acceleration is due to change in magnitude of tangential velocity and not because of change in direction. So which acceleration is there because of change in direction? It is the centripetal acceleration, right? So tangential acceleration is due to change in the magnitude of tangential velocity. Centripetal acceleration is due to change in direction of angular velocity. Okay, now so there are two kinds of accelerations in circular motion. So what will be total acceleration? It will be sum of those two. Okay, it is vector sum of tangential acceleration and centripetal acceleration. And if you want magnitude of the total acceleration in circular motion, it is square root of AT square, which is tangential acceleration square, plus AC square, which is centripetal acceleration square. Okay, so after that we will discuss about next important quantity, which is angular momentum. Okay, so just like the state of linear motion is defined by the linear momentum, the state of rotational motion is defined by quantity called angular momentum. So what is angular momentum? So if particle is moving with momentum, let's say p bar, its angular momentum is defined as r bar cross p bar, where r bar is the position vector of the particle. And if you are talking about a body, not a particle, then its angular momentum is given by this formula. It is I into omega. Okay. So the trick here is, if you want to go from linear motion to angular motion or rotational motion, what you have to do is just replace each quantity by its analogous quantity in rotational motion. Okay. So then you will get the formula for the quantity in rotational motion. So the analogous quantity of P is L. The analogous quantity of momentum is angular momentum. So momentum is mass into velocity. So if you want formula for angular velocity, the analogous quantity of mass in rotational motion is moment of inertia I, and analogous quantity of velocity is angular velocity. So L is equal to I into omega. All right. After that, so just like we have Newton's second law in linear motion, F is equal to what? dp by dt, the rate of change of momentum with respect to time. And if mass remains constant, then you can write it as F is equal to m into a. Okay, mass into acceleration. Just like that, in rotational motion, the state of motion is measured by angular momentum. So the Newton's second law for rotational motion is torque acting on a body. So torque is analogous quantity of force is equal to the rate of change of angular momentum with respect to time. Okay. So angular momentum is analogous quantity of the linear momentum. Okay. So angular momentum, as we have seen, it can be written as I into omega. You can take I out. Okay, if you take I out, because if it is constant, so you can take it out. So it will be I times d omega by dt. So d omega by dt is alpha. All right. So torque is equal to what? I into alpha. So just like you have force is equal to mass into acceleration, tau is equal to I into alpha. Okay. So this is Newton's second law for rotational motion. All right. And after that, there is law of conservation of angular momentum. Okay, so conservation of angular momentum. So if torque acting on a body is equal to 0, so if tau is equal to 0, then the L bar will be what? Constant. Torque is 0 means derivative of L with respect to t is 0. That means L is not changing, so L is constant. So if torque is 0, L remains constant or conserved, we can say. Okay, so this is law of conservation of angular momentum. Okay, and then there is one more thing, the kinetic energy of rolling motion. So if we have this body which is rolling on this plane, okay, then it performs two kinds of motion. Okay, so it is performing linear motion, it is moving in this direction with some velocity, and it is also rotating about itself. Okay, so rolling motion is combination of linear motion and rotational motion. So it has two kinetic energies associated with it. So one is kinetic energy due to translational motion or linear motion, you can say, and one is kinetic energy due to rotational motion. Okay, so kinetic energy of translational motion is half of mv square. Kinetic energy of rotational motion. So as I said, just replace the quantities with their analogous quantities. So analogous quantity of m is I, analogous quantity of v is omega. So kinetic energy in rotational motion is I into half of I into omega square. Okay, and if you add it up, okay, and if you substitute I is equal to mk square over here and omega equals to v upon r, if you substitute that, then you end up with this formula. So kinetic energy of rolling motion is half mv square multiplied by 1 plus k square upon r square. Okay, yeah. So after that we have velocity and acceleration of a body which is rolling down an inclined plane. So let's say we have a body which rolls down from this point, okay, from this topmost point. So what will be its acceleration when it rolls down? So it is g sine theta divided by 1 plus k square upon r square is the acceleration. And when this body reaches this point at the bottom, what will be its velocity? So its velocity at the bottom is given by square root of 2gh divided by 1 plus k square upon r square. Okay, so this we obtain when we equate potential energy at top equals to kinetic energy of rolling motion at the bottom. Okay, so V equals to square root of 2gh upon 1 plus k square upon r square, and its acceleration is g sine theta divided by 1 plus k square upon r square. Okay, these formulae we need to memorize. And now that we have seen all the formulae, let's solve some problems based upon these. And in yesterday's lecture we solved till this problem, so let's move on and solve some more problems. Okay, so a solid sphere of mass m and radius r is rotating about its diameter. A solid cylinder of the same mass and same radius is also rotating about its geometrical axis. Okay, so we have a solid sphere and a solid cylinder, they are rotating about their respective axis. So respective natural geometric axis. With then a solid cylinder of same mass and same radius is also rotating about its geometric axis with an angular speed twice as that of sphere. So angular speed of this cylinder is 2 times as that of the sphere. The ratio of their kinetic energies. So we want to find out ratio of their kinetic energies. So this is a simple problem. See, we want to find out energy of sphere divided by energy of cylinder. So it is I of sphere, sorry, E of sphere, energy of sphere divided by energy of cylinder. So we know formula for kinetic energy, it is half of I into omega square. So for sphere, I will write half of I of sphere into omega of sphere square, half of I into omega square, and for cylinder it is half of I of cylinder into omega of cylinder square. Now here, in order to solve this, we need to know the formula. Okay, so we need to know the formula for the moment of inertia. Okay, so it is half of moment of inertia of a sphere. What is moment of inertia of sphere? It is solid sphere, it is 2 by 5 mr square. into we have omega sp square divided by, it is half of moment of inertia of a cylinder. What is that? Moment of inertia of a cylinder is 1 by 2 mr square. Okay, and it's given that the of angular velocity of the cylinder is twice as that of sphere. Okay, so we can substitute that too. So it is 2 times angular velocity of this sphere square. So this thing will get cancelled out. Okay, this 2 gets cancelled out. So we have this 4 into denominator of denominator, so it goes into numerator. So we can write it as, so this is equal to 4 by 5. Okay, and here we have omega sp square divided by square of 2 times omega sp square, so which will be 4 times omega sp square. So this thing also gets cancelled and this 4 gets cancelled. So our answer is 1 by 5. Okay, so option B is the answer. So is it clear? All right. Let's move on to the next problem. The next problem is a light rod of length L has two masses m1 and m2 attached to its two ends. The moment of inertia of the system about an axis perpendicular to rod and passing through its center of mass is. So we had started solving this problem yesterday and there was a power cut. Okay, so anyways, we have two masses m1 and m2. This is first mass, this is second mass, and we want to find out moment of inertia of the system about axis perpendicular to the rod and which is passing through the center. So it is light rod. Light rod means there is no mass to the rod. Okay, so now see, first of all we have to find out the center of mass of the system. So let's suppose the distance of center of mass from m1 is x. So let's call m1, okay, this point as origin. So how much will be this much distance? This is L minus x, right? So we want to find out the position vector x coordinate of center of mass. So it will be what? So m1 into x1 plus m2 times x2 divided by m1 plus m2, right? So this xcm is, suppose it is equal to x, okay, m1 x1, so it is m1 times position of this first particle, okay, x coordinate of first particle is 0, okay, plus m2 times the x coordinate of second particle, it is equal to length of the rod divided by, we have m1 plus m2. Okay, so we got the value of x, okay, which is m2 times L, because this term is 0, so it is m2 times L. So we got x equal to m2 times L upon m1 plus m2. Okay, so now what is the moment of inertia of this system about this point, about an axis which passes through this point, okay, like this. So to find moment of inertia, it is what? It will be, okay, so I equals to m1 into distance of first particle from this point, which is x, okay, x square, plus m2 multiplied by distance of this particle from here. Okay, so it is m2 times L minus x square, and then we have to substitute x and there will be long calculation. M1 times what is x? It is m2 into L upon m1 plus m2, and we have square of that, plus we have m2 into L minus x. So L minus m2 into L. Let's substitute x. Okay, m2 into L upon m1 plus m2, and we have square of that. I hope it is not going out of screen. It's not going. Yeah. So it is m1 m2 upon m1 plus m2 square into L square. That's first term, plus second term is m2, and here we have to multiply this, multiply and divide L with m1 plus m2. Okay, so let's do that. It is m2 multiplied by m1 into L plus m2 into L divided by m1 plus m2. Okay, so what I have done is I have multiplied and divided this L with m1 plus m2. Okay, because I want to make denominator of these two terms common. Okay, then we have minus m2 into L upon m1 plus m2, and then we have square of this. Okay, whole bracket. So something gets cancelled. M2 into L upon m2 into L gets cancelled because we are, this denominator is same, and we are subtracting second term from this first term. Okay, so m2 times L gets cancelled, and we are left with m1 into L. Okay, yeah. Oh, in this first equation it will be m2 square, right? I'm squaring this, so it will be this m2 squared. Okay, then here I will get m1 into L square of that divided by m1 plus m2 square. So it is m1 square. Okay, so let's add a page. So I is equal to m1 m2 square L square upon m1 plus m2 square, plus from second term it is m2 into m1 square L square divided by m1 plus m2, and we have square of this. Okay, so now we can take something common. So let's check answers. So we have, okay, let's take m1 m2 common from these two terms. So if we take m1 m2 common, let's take m1 m2 into L square common. So we are left with m2 from first term, plus in second term if we take m1 m2 common, it will be m1. Okay, we are left with m1 from the second term, and in denominator we have m1 plus m2 square of that. So this thing gets cancelled with the square, and we are left with what? m1 m2 upon m1 plus m2 into L square. So this is the answer. Let's check. m1 m2 upon m1 plus m2 into L square. So option B has to be the answer. Okay. All right. Then let's move on to the next problem. So next problem is the ratio of radii of gyration of a circular disk to that of circular ring, each of same mass and radius about their respective axis is. So we have a circular disk, okay, a disk like this, and a circular ring, a ring, okay, and we want ratio of their radii of gyration. Okay, they have same mass and same radius. Okay, so what is moment of inertia of a disk? It is half of mr square. What is moment of inertia of a ring? It is half of, it's not half, it is m into r square. Okay, and you want radius of gyration. So this moment of inertia can be written as what? This is equal to moment of inertia of this disk in terms of radius of gyration can be written as uh, m into k square, m into k of disk square. Okay, all right. So from there we can find out the radius of gyration of disk. Okay, or yeah, let's do that. So this thing gets cancelled out, m and m gets cancelled out. So k disk is equal to, okay, it will be k square, mk square it is. Okay, so you get k of disk is equal to what? R upon root 2. Okay, if you take square root on both sides, so k disk will be what? So r square upon 2 equals to k square. So k equals to what? R upon root 2 if you take square root. So for ring, moment of inertia in terms of radius of gyration can be written as mk square equals to mr square. Okay, so this is for k of ring. So gets cancelled out and you get k of r, k of ring is equal to what? R. So if you take ratio of them, okay, if you take ratio of the radius of gyration of a disk to the ring, okay, so this divided by, if you take radius of gyration of a ring, so which is equal to what? R. So I will divide this equation by this equation, right? So what do I get? R gets cancelled out, okay, and you are left with 1 upon root 2. So what is the ratio? Ratio is 1 upon root 2. Option D is the answer. Okay, after that, let's see next problem. The moment of inertia of a thin rod of mass m and length l about an axis passing through its midpoint and perpendicular to its length is IO. Its moment of inertia about an axis passing through one of its ends and perpendicular to its length is. Okay, so we have a thin rod. All right, thin rod, and its moment of inertia we want to find out about an axis passing through one of its ends and perpendicular to its length. Okay, so we want to find out its moment of inertia about this axis, right? Passing through one of its ends and perpendicular to its length. And it's given that moment of inertia about this axis is IO. Okay, so we have parallel axis theorem, right? So this distance we know it will be L by 2. So what does parallel axis theorem say? So parallel axis theorem, it says that moment of inertia about this axis, let's call it, let's say point A, IA is equal to IC plus MH square. What is IC? It's the moment of inertia about a parallel axis which passes through the center of mass. Okay, so this is equal to, this is given that moment of inertia about this axis which passes through its center of mass is IO. So it's IO plus m into h square. Now what is h? H is this distance, so which is L by 2. Okay, so L by 2 and we have square of that. Okay, so what is L by 2 square? It is L square upon 4. So IO plus we have m into L square divided by 4. So this is moment of inertia about this axis which passes through its end and which is perpendicular, sorry, which is parallel to this axis which passes through its center of mass. Okay, so this was another simple question. All right, so let's move on to the next question. So we have four identical thin rods, each of mass m and length small l, form a square frame. moment of inertia of this frame about an axis through the center of the square and perpendicular to its plane is. So we have four thin rods of mass m and length l. They form a square frame. Okay, and so let's draw that square frame. So the frame is something like this, and we want moment of inertia of this frame about an axis which passes through the center of the square. Okay, so this is center of the square, and the axis is perpendicular to the plane. Okay, so it is perpendicular to this plane at this point. Okay, so if I try to draw kind of 3D diagram, so it will be, this is suppose the square, and the axis passes through its center. So we want to find out its moment of inertia about this axis, right? So how do we do that? So now see, let's consider any of these rods. We have four rods. Okay, so let's consider, let's say this rod. Okay, we'll use this color. So if I consider this rod, so what is its moment of inertia? So I know moment of inertia of this rod about, let's say, this axis, this vertical axis which passes through its center of mass. I know moment of inertia about this axis, right? So this is suppose IC, and if I use now parallel axis theorem, so this is distance h. Okay, so I know, let's say, moment of inertia about this axis which passes through this point. Okay, so this is IC, and I want moment of inertia of this rod. Okay, this rod about this point. Okay, so this distance is h. I have shown it in two diagrams. This distance is h. It is this distance in this diagram. Okay, so we know IO, let's say moment of inertia about this axis is IO. Okay, so IO is equal to IC plus mh square. And what is IC? So moment of inertia of a thin rod about an axis which passes through its center of mass is given by what? It is ml square divided by 12. And okay, so we have m into h square. What is h? So h is this much distance. So if L is length of this rod, okay, it is half of that. Okay, because this is center of the square. So m into L by 2 square we have, and then it is ml square divided by 12 plus m into L by 2 square, which will be ml square upon 4. Okay, so now we'll make denominators common. So this is ml square by 12 plus, we have to multiply and divide by 3 over here. So it will be 3 times ml square upon 12. So it is equal to what? 1 ml square upon 12 plus 3 ml square upon 12. So it is 4 ml square upon 12. Or you can divide this 12 by 4. So it will be 3. So IO equals to ml square divided by 3. And there are 4 such rods. Okay, there are 4 such rods over here. So it is going to be what? 4 times of this. So it is 4 times of mi of square equals to 4 times ml square divided by 3. So this one will be the answer. Okay. So yes, is it clear? Yeah, I guess so. So let's move on to the next problem. Okay, this problem is also based upon moment of inertia. So a thin rod of length L and mass m is bent at its midpoint. So you have a rod, you bend it at its midpoint into two halves so that the angle between them is 90 degrees. Okay, so this is the rod. Okay, and you break it, you actually bend it about the midpoint, about this point, and you form a rod like this. Okay, angle between these two halves is what? It is 90 degrees. This is 90 degrees. Okay, so you want to find out moment of inertia of this bent rod. So this rod you have bent, you have to find moment of inertia of this bent rod about axis passing through the bending point. So about this point, and perpendicular to plane. Okay, so axis is perpendicular to this plane. All right, so it is defined by two halves. All right, it is perpendicular to this plane. So we know, let's think about any one of those rods. So let's think about this one. So now if we consider this half rod only, its moment of inertia about this point will be what? So its weight, its mass is suppose m dash. Okay, so for this one m dash will be equal to what? Length of the rod is L, and you have broken it down into two parts. Not broken, you have bent it. So the mass of one of them will be what? M by 2. Okay, so this is total mass is m, you bend it in two parts, so mass of this one will be m by 2, mass of this one will be m by 2. Okay, and what about length? L dash is also L by 2. And then we know moment of inertia about this point. Okay, about midpoint. So moment of inertia of one of those two rods, let's call it I dash, will be what? It is m dash L dash square upon 12. Okay, this is the formula. Okay, we need to remember. So it is m by 2 into L square by 12. Okay, so it is L dash, which is L by 2 square upon 12. Okay, and if you solve this, you will get some value. But just in last problem, we found moment of inertia about this point. So what is moment of inertia about an edge? We found it here. So for a rod, it is what? ml square divided by 3. Okay, it's here. So if you have a rod, its moment of inertia about the edge, okay, it is ml square divided by 3. So now because we solved it in last problem, we have to do same thing over here. So here it is m prime, okay, m dash L dash square upon 12. So you have to find its moment of inertia about this axis. So it will be what? Let's call it I dash. So it will be m dash L dash square divided by 3. So because we have solved this in last problem. Okay. So all right. So what do we get? So for one rod, I dash will be equal to what? Okay, I'm talking about moment of inertia about this point. So yeah, not this thing. Okay, not moment of inertia about the center of mass. Okay, so it will be m dash L dash square upon 3, which is m by 2 into L by 2 square divided by 3. Okay, so that is L by 2 square is L square divided by 4, and okay, it is m by 2 into L square upon 4 into we have 1 by 3. So this is 4 times 3 is 12, 12 times 2 is 12 times 2 is 24. So we have ml square upon 24. So this is for one of these rods, right? And we have two rods, two such rods, okay, because we have bent this big rod into two parts, okay. So mi of bent rod will be equal to what? 2 times of I dash, so which is 2 times of ml square divided by 24, and that is ml square divided by 12, okay, should be ml square upon 12. Yeah, so option D should be the answer. All right, okay, then let's move on to the next problem. So the next problem is the moment of inertia of a uniform circular disk of radius r and mass m about an axis touching through the disk and diameter at its diameter are normal to the disk is. So we have a disk over here, okay, and we want to find out its moment of inertia about this axis which touches the disk. All right, so this is simple problem. We know its moment of inertia about this axis which passes through its center, okay. So if we use the parallel axis theorem, so moment of inertia about this point is IC. So moment of inertia about this axis is suppose IO. So we know that IO is equal to IC plus m into h square, which is equal to IC is, we know moment of inertia of a disk is given by mr square upon 2 plus we have mh square. What is h? It is distance between these two axes, okay. So what is mh square then? It is m into r square. So mr square divided by 2 plus mr square, it gives us 3 by 2 mr square. This is I. All right. Okay, so this is another simple problem. Okay. Then let's move on to the next problem. So next problem is a wheel has angular acceleration of 3 radians per second square and initial angular speed of 2 radians per second. Okay. In a time of 2 seconds, it has rotated through an angle. This is the question. So it has angular acceleration, it's given, and initial angular speed is also given, it is 2 radians per second. So this is very simple problem, okay. We are asked about the angle through which it rotates. So theta is equal to omega naught times t plus half of alpha into t square, okay. So because it is rotating with constant angular acceleration, what is omega naught? It is 2 radians per second. So 2 times time is 2 plus half of, how much is alpha? Alpha is 3. So 3 into time is 2, so 2 square. Okay, so 2 times 2 is 4. So 4 plus we have this 2 square divided by 2 will give us 2. So 2 times 3 is 6. So 6 plus 4. Okay, so answer is 10 radians. This is very simple problem. So its answer is what? 10 radians. All right.